Have you ever wondered how the raw stuff of the universe becomes the matter in your hands? Start with a cloud of hydrogen and helium, thin as breath. Gravity nudges it inward. Pressure climbs. Heat rises. In the core, simple nuclei begin to fuse, and new elements appear: helium from hydrogen, then carbon, oxygen, and beyond. Each step follows clear rules: density, temperature, cross-sections, energy released as light. What begins as a quiet burn becomes a factory that sets the periodic table in motion. Listen for the through line: how mass determines a star's fate, how that fate decides which elements exist, and how those elements later build planets and life. If this steady path from first principles to familiar matter speaks to you, a like and subscribe helps others find it. Settle in. We'll follow the reactions all the way. Let's begin with the simplest picture the universe can offer. Almost all normal matter was hydrogen and helium, with a trace of lithium. Normal matter here means atoms built from protons, neutrons, and electrons, the stuff that forms gas, stars, planets, and people. After the Big Bang, space expanded and cooled. In the first few minutes, protons and neutrons began to join. This short window is called Big Bang nucleosynthesis. It produced large amounts of hydrogen, a good share of helium, and a tiny amount of lithium. Heavier elements did not survive the heat and rapid motion of that era. The result was a young universe filled with thin clouds of these light atoms. Expansion continued. Cooling continued. Gravity, which pulls mass toward mass, began to gather the gas. A cloud that had a little more density than its surroundings pulled in even more gas. Growing slowly, the fall inward converted gravitational energy into heat. The center became hot and dense. When the core passed a critical temperature and pressure, the conditions allowed nuclear fusion. Fusion means that light atomic nuclei can push close enough to stick together, forming heavier nuclei and releasing energy. The star had turned on. The first and longest stage for most stars is hydrogen fusion. In the Sun, hydrogen nuclei single protons combine through a chain of steps to make helium. A small part of the mass turns into energy, as described by the relation E equals mc squared. That energy is carried outward by photons and, in the outer layers, by moving gas. It reaches the surface and escapes as light and heat. The star does not collapse because radiation and hot gas push outward while gravity pulls inward. This balance is called hydrostatic equilibrium. As long as the fuel in the core is hydrogen, the star remains stable for a very long time. Not all stars live the same way. Mass sets the pace. Massive stars start hotter, burn fuel faster, and shine brighter. They live millions of years. Low-mass stars start cooler, burn hydrogen slowly, and can live for tens or even hundreds of billions of years. The Sun sits in the middle range with an expected main sequence lifetime of about 10 billion years. A small, cool red dwarf spends its life in careful use of hydrogen. A very massive blue star races through its fuel. While hydrogen burns in the core, the star keeps a steady output. Over time, hydrogen becomes helium, ash, in the core. Hydrogen may still burn in a shell around the center, but the center itself becomes dominated by helium. Without the same fusion support, the core contracts under gravity. The contraction heats the core until helium fusion becomes possible. Helium nuclei, also called alpha particles, join to form carbon. At higher temperature, some of that carbon can capture helium to form oxygen. These reactions require more heat and higher density than hydrogen fusion, so they happen later and only when the core conditions allow it. In more massive stars, this pattern repeats. When helium runs low, the core contracts and heats again. Carbon confuse to form neon, sodium, and magnesium. Oxygen confuse to form silicon and sulfur. Silicon confuse to produce iron and nearby elements. The structure of such a star looks like layers in an onion, with different elements fusing in shells at different depths. Each layer has its own temperature range and reaction pathways. The timescales shrink as the elements grow heavier. A massive star can spend millions of years fusing hydrogen, but only thousands of years on helium, years on carbon, months on neon, weeks on oxygen, and mere days on silicon. Iron marks a hard stop for normal fusion in stellar cores. Fusing iron or heavier elements does not release energy. It absorbs energy. That breaks the balance. When a massive star builds up an iron core beyond a certain mass, the core can no longer support itself. Electrons get forced into protons to form neutrons, and the core collapses in a fraction of a second. The outer layers crash inward and then rebound. A shock wave forms. Neutrinos, tiny particles that barely interact, carry away huge amounts of energy and help drive the shock. The result is a core collapse supernova. In this violent event, elements made during the star's life are flung into space. New, heavier elements can also form in the intense flow of neutrons and in the shock-heated layers. The star leaves behind a neutron star, or, if the mass is high enough, a black hole. Lower mass stars end differently. A star like the Sun will never reach the conditions needed to fuse carbon. After helium fusion in the core ends, the outer layers puff out and the star becomes a red giant. Pulses and winds remove the outer gas, leaving a hot core behind. Ultraviolet light from the exposed core makes the ejected gas glow as a planetary nebula. The core cools and settles as a white dwarf, an object the size of Earth, but with a mass similar to the Sun's, supported by electron pressure. A white dwarf no longer fuses elements. It radiates away its stored heat over many billions of years, growing dimmer and cooler. The nebula disperses. The gas returns to interstellar space. These endings matter because they are how the heavy elements spread. Oxygen, carbon, and nitrogen, forged in stellar cores and shells, are mixed back into space by winds and by supernovae. Silicon, sulfur, calcium, and much of the iron group come from supernova explosions, and also from a different kind of event, the thermonuclear supernova, known as type Ia. A type Ia supernova occurs when a white dwarf in a close binary system gains mass from a companion star. If the white dwarf approaches a critical mass, carbon in its interior ignites almost at once, and a runaway fusion process unbinds the star. The explosion produces large amounts of iron and nickel and spreads them widely. Over many generations of stars, these processes raise the metallicity, which in astronomy simply means the fraction of elements heavier than helium. There is more than one way to make the heaviest elements. Elements like gold, platinum, and uranium require rapid neutron capture, known as the R process. For a long time, core collapse supernovae were proposed as the main site. Recent multi-messenger observations, gravitational waves, and light measured together have shown that merging neutron stars can also power the R process. When two neutron stars spiral together and collide, they eject neutron-rich matter. That matter expands and cools, and heavy nuclei build up rapidly. The glow from these decays is called a kilonova. The data from such events support the idea that a large share of the universe's heaviest elements come from neutron star mergers. Supernovae may still contribute, but the balance is an active area of research. Return to the beginning to see the chain. Big Bang nucleosynthesis set the initial mix. Gravity gathered gas to form stars. Fusion in stars built elements up to iron and a bit beyond, depending on conditions. Explosions and winds returned those elements to space. Later generations of stars formed from gas already enriched by earlier stars. Planets formed in disks around young stars from this mixed material. On at least one planet, chemistry and energy flows led to life. None of this required more than the laws of physics, operating in many places for a long time. Hydrogen deserves a clear note. It is a single proton with a bound electron. In stars, the main fusion paths are the proton-proton chain, and, in hotter cores, the carbon-nitrogen-oxygen cycle. Both paths turn hydrogen into helium, releasing energy. The proton-proton chain dominates in stars like the Sunday. The CNO cycle becomes more important in higher mass, hotter stars. Helium, with 2 protons and usually 2 neutrons in its nucleus, is both a product and later a fuel. When helium fuses, the triple alpha reaction forms carbon. Adding another helium can make oxygen. Lithium is a special case. The amount made in the early universe is small, and the observed amounts in old stars do not always match simple predictions. Some stars destroy lithium in their envelopes. Some processes can create it later. This lithium problem is a useful reminder that even simple elements can bring hard questions. Energy transport inside stars is also part of the story. Near the core, photons scatter many times before escaping, a process called radiative diffusion. Farther out, in cooler layers, gas can carry energy by rising and sinking, which is convection. The mix of these processes affects how a star evolves and how it loses mass. In very massive stars, strong radiation pressure drives winds that remove surface layers. In red giants, convective envelopes can dredge up newly made elements and release them. These flows help set the chemical makeup of the gas between stars. Timescales are vast, but the steps are regular. A cloud collapses in a few million years to form a star. A sun-like star lives on hydrogen fusion for billions of years. A massive star may live fast and die young, returning material to space quickly. In a galaxy, many such cycles overlap. Star formation, feedback from winds and radiation, and the shock waves from supernovae shape the gas. Dense regions cool and collapse again, and new stars light up. With each cycle, the average level of heavy elements rises. We can measure this trend by looking at the spectra of stars. How they absorb and emit light at specific wavelengths reveals their chemical content. Gravity is the quiet driver throughout. It gathers gas to start stars. It holds stars together against their own heat until fusion produces enough pressure. It compresses cores when fuel runs low, triggering the next stage. When support fails, gravity collapses the core and launches an explosion. Even after a star's death, gravity shapes the fate of the remnant. A neutron star remains stable because neutrons resist further compression. A black hole forms when no known pressure can stop collapse. The simple early mix of hydrogen and helium was not a limitation. It was a practical starting point. Hydrogen is easy to fuse and abundant. Helium is stable and durable. Together they allowed long, steady energy sources to exist. Long-lived stars provide the time needed for galaxies to assemble, for planets to form, and for slow processes to run. The gradual buildup of elements is not flashy, but it is reliable. It follows from basic rules: conservation of energy and momentum, quantum tunneling that lets nuclei fuse despite electrical repulsion, and the way nuclear binding energy changes with atomic number. When you trace an atom in your body back through time, you find many paths that converge in stars. The oxygen you breathe likely formed in a massive star and was released when that star ended its life. The calcium in your bones can come from supernovae and from the later burning stages of past stars. The iron in your blood is a classic product of both core collapse and thermonuclear supernovae. The carbon that forms the backbone of organic molecules comes from helium fusion in earlier generations of stars. Each of these elements has a typical origin, but any given atom has a long and mixed history in interstellar space before it was gathered into the cloud that formed the sun and the planets. It is useful to keep scale in mind. A stellar core where fusion runs is dense and hot, millions to hundreds of millions of degrees, and densities many times higher than water. The sun's core is about 15 million degrees and carries pressures we can only describe with exponents. A teaspoon of neutron star matter would outweigh mountains. These numbers can feel distant, yet they arise from familiar forces scaled up: gravity pulling, pressure pushing back, and heat moving from hot regions to cooler ones. The observational side agrees with this picture. We see the elemental fingerprints in starlight. We watch supernovae in far-off galaxies and measure how their light curves evolve, telling us about the material created. We detect gravitational waves from merging compact objects and observe the afterglow that reveals new heavy elements. We measure the cosmic microwave background to check the amounts of hydrogen and helium predicted from the early universe. We map the chemical patterns across the Milky Way to learn how star formation has changed over time. Each method adds a piece, and together they form a consistent account of how stars forge the elements. The path from simplicity to complexity is steady, not sudden. It begins with light nuclei made easily in a hot, expanding young universe, and then slows into long eras where gravity gathers gas and stars take over. Inside those stars, fusion does the shaping. Short, energetic events, winds and supernovae, then carry the new nuclei back into space. The cycle repeats, enriching galaxies and supplying the raw material for planets. You can see the results everywhere, from basalt on the seafloor to the oxygen in the air. Each star is a hot, dense engine that makes this cycle work. Its power source is fusion, small atomic nuclei pressed so close together that they join into something heavier. The story starts with hydrogen, the simplest atom, one proton with one electron. In a star's core, 4 hydrogen nuclei become one helium nucleus through a chain of steps. The totals do not quite match. A little mass goes missing and reappears as energy. That energy leaves as light and heat, the outward sign that the quiet, patient chain from simple beginnings to complex matter is still running. Getting hydrogen nuclei to join is not easy. Protons carry positive charge and push away from each other. Inside a star, the temperature climbs to millions of degrees and the pressure is extreme. At those conditions, particles move so fast and crowd so tightly that some pairs get close enough for the strong nuclear force to act. This force does very little at normal distances, but at very short range, it pulls protons and neutrons together with great strength. Quantum tunneling, a An effect where particles cross barriers they could not cross classically also helps. Together, heat, pressure, and tunneling make fusion possible and steady. While hydrogen fuses, a star holds itself in balance. Gravity pulls inward. Hot gas and the flow of radiation push outward. This balanced state is called hydrostatic equilibrium. As long as hydrogen fuel remains in the core, the balance lasts. The Sun is in this long phase now. A more massive star burns fuel faster and shines brighter. A smaller star burns fuel slowly and glows gently for far longer. In all cases, mass sets the pace. Hydrogen does not last forever. Over time, the core fills with helium, ash. Hydrogen continues to fuse in a shell around the core, but the center itself stops producing outward pressure from hydrogen reactions. The core contracts under gravity, which raises the temperature. When it becomes hot and dense enough, helium fusion can begin. Helium fusion is harder to start because helium nuclei carry twice the positive charge of hydrogen nuclei. The first important step is called the triple alpha process. 3 helium nuclei, in quick sequence, form 1 carbon nucleus. Sometimes carbon captures another helium nucleus and becomes oxygen. These 2 elements, carbon and oxygen, are key parts of life, and stars produce them in bulk. In stars with much greater mass than the Sun, the pattern continues. After helium runs low, the core contracts and heats again. Carbon can fuse to form neon, sodium, and magnesium. Oxygen can fuse to form silicon and sulfur. Silicon can fuse to make elements near iron. The interior of such a star looks layered. Hydrogen burns in an outer shell. Helium burns beneath it, then carbon, then oxygen, then silicon. Each layer at the temperature it needs. The timescales get shorter with each step. Hydrogen burning lasts millions of years in a massive star. Silicon burning may last only days. Iron changes the rules. Fusing lighter elements than iron releases energy. That energy supports the star. Fusing iron or anything heavier requires energy. When a massive star builds up an iron core with no new energy source, gravity wins. Electrons are forced into protons, neutrons form, and the core collapses in a fraction of a second. The inward rush stops abruptly when the core becomes almost pure neutron matter. A shockwave forms and moves outward. Neutrinos, tiny, weakly interacting particles produced in large numbers, carry energy from the core and help the shock push through the star. The result is a core collapse supernova. Many elements the star made during its life are blown into space. In the shock and in neutron-rich layers, new heavy elements form quickly by capturing neutrons before they can decay. Not all stars end this way. A star like the Sun will never get hot enough to fuse carbon in its core. After the helium phase, its outer layers expand and cool, and it becomes a red giant. Pulses and winds carry the outer gas away. The exposed hot core lights this gas and makes a glowing shell called a planetary nebula. The leftover core becomes a white dwarf, about Earth-sized and very dense. It shines by stored heat and slowly cools for billions of years. The gas returns to space and mixes with other clouds. White dwarfs can also end in another kind of explosion. In a tight binary system, a white dwarf may pull matter from a companion star. If the white dwarf grows toward a critical mass, carbon in its interior ignites nearly everywhere at once. The result is a thermonuclear supernova. also called a Type Ia supernova. It tears the star apart and makes large amounts of iron group elements, which it spreads across its host galaxy. Because many Type Ia supernovae have similar peak brightness, astronomers use them to measure distances. Chemically, they are major sources of iron and nickel. The heaviest elements such as gold, platinum, and uranium need a different path. They form when nuclei capture neutrons very quickly, a process called the R process. For decades, scientists debated the main site. Core collapse supernovae were candidates. Recent observations of gravitational waves and light from a neutron star merger showed that these collisions are rich R process factories. When two neutron stars spiral together and collide, they eject neutron-heavy matter. As that matter expands and cools, nuclei capture neutrons in rapid chains and build up to very heavy elements. The radioactive decay of these new nuclei powers a glow called a kilonova. This evidence points to neutron star mergers as major sources of some of the rarest elements in the periodic table. With these pieces, the big picture is clear. The early universe made hydrogen and helium with a trace of lithium. Gravity gathered this gas into stars. Fusion built elements up to iron in stellar cores and shells. Supernovae and neutron star mergers made many heavier elements and spread them. Stellar winds and gentle outflows also returned carbon, nitrogen, and oxygen to space. Gas enriched by past stars formed new stars and planets. Over many cycles, the average level of heavy elements in a galaxy rose. This slow enrichment is why younger stars like the Sun contain more oxygen, silicon, and iron than the oldest stars in the Milky Way's halo. It helps to link this story to the periodic table. The table is a map of atomic structure, but it also reflects origin. Hydrogen and helium belong to the first row and were made in the first minutes after the Big Bang. Carbon, nitrogen, and oxygen, the core of biochemistry, come from helium fusion and later burning in stars. Silicon, magnesium, and sulfur are common in rocks and are products of advanced burning in massive stars. Iron and nickel come from the final stages of massive stars and from thermonuclear supernovae. Beyond iron, many elements owe much of their abundance to the R process in neutron-rich explosions and mergers. When you look at the table, you can read a history of where and how the entries formed. Some details need simple definitions. A nucleus is the center of an atom made of protons and neutrons. An isotope is a version of an element with the same number of protons but a different number of neutrons. Metals in astronomy means any element heavier than helium. A spectrum is the pattern of light spread into colors or wavelengths. Dark or bright lines in a spectrum tell us which elements are present because each element interacts with light at specific wavelengths. Astronomers use spectra to measure the contents of stars and gas clouds. Those measurements agree with the idea that stars are the main forgers of the elements. Energy does not travel the same way in every part of a star. In some regions, photons carry energy outward by many small steps, scattering again and again. This is radiative transport. In other regions, gas carries energy by rising when hot and sinking when cool. This is convection. The balance of radiation and convection depends on mass, temperature, and composition. It affects how stars mix their interiors, how they lose mass, and how long each stage lasts. In red giants, convection can dredge up newly made elements and enrich the surface. In hot, massive stars, strong radiation pushes on the outer layers and drives winds that peel off mass over time. Timescales are very different from human experience. A gas cloud may take 1,000,000 years to collapse into a cluster of stars. The Sun will spend about 10 billion years fusing hydrogen. A star with 10 times the Sun's mass may live 20 million years or less. The briefest stages are still long on our scale. A week of silicon burning in a massive star is both a blink in stellar terms and a span longer than any human lifetime. These long periods allow structure to grow and chemistry to become complex. Fusion stops at iron in a normal star because of nuclear binding energy, the energy that holds a nucleus together. Binding energy per nucleon, per proton or neutron, increases up to iron and nickel. Fusing lighter nuclei increases binding energy and releases the excess as heat and light. Fusing heavier nuclei would reduce binding energy and absorb energy. This simple curve explains why stars can shine by fusion only up to a point, and why more extreme events are needed to make the heaviest elements. The Sun's path is straightforward. It will continue fusing hydrogen in its core for several billion years. Later, it will expand into a red giant, fuse helium into carbon and oxygen in its core, and then shed its outer layers. The remnant will be a white dwarf made mostly of carbon and oxygen. Our star will not make iron in its core and will not explode as a core collapse supernova. Yet even without that, it contributes to galactic chemistry through winds and the ejection of its outer layers, which carry freshly made carbon and nitrogen into space. Observations across many tools support this framework. Telescopes record supernova light curves and spectra that reveal which elements were produced. Space observatories see gamma-ray lines from radioactive decay of freshly made nuclei in supernova remnants. Detectors on Earth measure gravitational waves from neutron star mergers, and follow-up telescopes observe kilonova light that matches models of heavy element formation. Surveys of stars map how the amounts of elements change with location and age in the Milky Way. The pattern is consistent. Older, metal-poor stars show lower amounts of heavy elements. Younger stars, born from recycled gas, show higher amounts. This agreement between theory and observation is a strong test. When you connect the dots, the role of stars becomes practical rather than poetic. Stars are long-lived power sources that also act as factories. They turn hydrogen into helium, helium into carbon and oxygen, and if massive build up to iron. When they die, they return material to space, where gravity can gather it again. The periodic table is the record of what those factories can make under different conditions. The pattern of abundances in planets and in living things follows from that record. Water is common because hydrogen and oxygen are common. Rocky planets are common because silicon, oxygen, magnesium, and iron are common. Trace elements that matter to biology exist because rare events seed galaxies with small but non-zero amounts of them. The chain from simple to complex is slow but dependable. A few rules guide it. Gravity gathers gas, fusion builds new elements, explosions spread them, and time lets the cycle run again. With each pass, clouds grow richer in the ingredients that make solids, oceans, atmospheres, and biology. Your own atoms record that path. Carbon and oxygen likely came from massive stars. Iron arrived in supernova debris. Calcium and silicon formed in late-burning shells. Trace elements iodine, zinc, and others carry signatures of rare, neutron-rich events. This is why the mix inside you matches what telescopes read in starlight and in the remains of stellar blasts. Set that picture next to the periodic table, and a quiet link appears. The rules that build stars also shape the atoms in you. Start with carbon. It does not dazzle like gold. stand out like oxygen in breath, or dominate like hydrogen. Yet it is the main framework of life. Without carbon, DNA would not chain, proteins would not fold, sugars would not store and move energy, and forests would not rise. Carbon works because each atom bonds cleanly in 4 directions, making strong links that form chains, rings, and branching networks. That simple flexibility lets small parts assemble into complex systems. The path that makes carbon starts in stars that have moved beyond hydrogen burning. When the core runs short on hydrogen, gravity squeezes it. Temperature and pressure climb. Around 100 million degrees, helium nuclei, also called alpha particles, begin to fuse. The key step is the triple alpha process. First, 2 helium nuclei form a short-lived nucleus of beryllium-8. It normally falls apart in a tiny fraction of a second. If, before it decays, a 3rd helium nucleus collides and sticks, the 3 become a stable carbon 1,2 nucleus. The odds of this sequence are small, but the core is hot and dense and filled with helium, so it happens often enough to matter. A special energy state in carbon 1,2 helps this reaction occur. Without it, carbon would be rare. This is not mysticism. It is nuclear structure lining up so that 3 small pieces can make one bigger, stable piece inside a hot, crowded core. Stars do not keep what they make. They shed material in winds and, for larger stars, in supernova explosions. Gentle outflows from aging, moderate mass stars carry carbon-rich dust into space. Violent deaths of massive stars eject carbon along with oxygen, silicon, and heavier elements. These atoms mix into interstellar clouds. Over time, gravity gathers the clouds again, and new stars and planets form from enriched gas. In this way, carbon made in one generation becomes raw material for the next. Carbon's chemistry explains its central role. Each carbon atom has 4 electrons available for bonding, so it can make 4 strong covalent bonds. It can link to other carbon atoms or to hydrogen, oxygen, nitrogen, and many more. Long chains make the skeletons of fatty acids and many polymers. Rings form sugars and bases in DNA. Branches and double bonds create variety in shape and function. Graphite is carbon in flat sheets that slide easily. Diamond is carbon in a rigid 3-dimensional lattice, which is why it is so hard. Carbon can also form hollow cages called fullerenes and narrow tubes called nanotubes. The same element builds soft pencil lead and cutting drill bits because the pattern of bonds is different. Life on Earth uses this versatility everywhere. Carbon forms the backbone of DNA, which stores and copies genetic information. It forms amino acids, which link to make proteins the active machines of cells. It builds carbohydrates, which store energy and form structures. It shapes lipids, which make cell membranes. Carbon dioxide, 1 carbon with 2 oxygens, is both a waste of breathing and a key input for plants. Through photosynthesis, plants and some microbes use light to turn carbon dioxide and water into sugars and oxygen. Animals eat the sugars, use oxygen to release energy from them, and breathe out carbon dioxide again. The same element cycles through air, water, soil, and living tissue in a steady loop. That loop extends into rocks and oceans. Carbon dissolves in seawater and forms bicarbonate and carbonate ions. It combines with calcium to make limestone. Volcanoes and weathering move carbon between Earth's interior, the ocean, and the air. Over long times, this cycle helps regulate climate by adjusting how much carbon stays in the atmosphere. When the cycle is in balance, temperatures and ocean chemistry stay within ranges that living systems can handle. When the cycle is pushed by rapid carbon release or removal, the climate shifts and ecosystems must adjust. The element that enables life is also a key lever in the planet's stability. Every carbon atom in your body once came from a star. Some were forged in a quiet helium-burning core. Some rode shockwaves from exploding stars. They drifted through space, joined a cloud, became part of the material that formed the sun and earth, and entered the chain of chemistry that led to cells. Alternative life chemistries are often discussed. Silicon is a common example, but silicon's bonds are less flexible in water and its long chains are less stable. Carbon's set of properties fits well with liquid water and moderate temperatures. That fit is why carbon chemistry, organic chemistry, is the default path for life on Earth and the main target in the search for life elsewhere. Oxygen sits beside carbon in this story and is just as central. You breathe it, drink it, bound into water, walk on it, locked into rocks, and rely on it in your cells to release energy from food. Its origin also lies in stars. Once a core has made carbon, helium nuclei can add to those carbon nuclei and make oxygen 1,6. This step needs higher temperature than the triple alpha process. But massive stars reach those conditions. Oxygen is stable, and stars produce a lot of it. In the universe as a whole, oxygen is the third most abundant element after hydrogen and helium. Stars return oxygen to space in two main ways. Moderate mass stars lift and shed layers during their giant phases, exposing material enriched by helium burning. Massive stars end in core collapse supernovae, which blast oxygen and many other elements outward at high speed. Over time, this oxygen becomes part of new clouds, new systems, and new planets. Earth inherited a large supply. Oxygen bonded with silicon to form silicates, the basis of most crustal rocks. It bonded with iron to form oxides. It bonded with hydrogen to make water, free oxygen gas, O2, in the air came later. Early Earth's atmosphere contained very little free oxygen. Microbes evolved photosynthesis that splits water using sunlight, releasing oxygen as a byproduct. At first, the oxygen reacted with dissolved iron in the oceans, forming layers of iron oxide that later became iron ore. Only after the reactive sinks filled did oxygen begin to build up in the air. This rise, called the Great Oxidation Event, changed Earth's surface chemistry and opened the door to oxygen-using metabolism. Oxygen allows cells to extract far more energy from sugars than earlier anaerobic processes. With more energy per unit of food, larger and more complex bodies became possible. Oxygen's behavior makes these roles possible. It forms strong bonds with many elements and can exist in several forms, including O2 and ozone, O3. In water, oxygen helps make a liquid that dissolves many substances and supports fast chemistry. In rocks, oxygen forms stable minerals that shape continents and ocean floors. In your blood, oxygen binds to iron atoms in hemoglobin, sticks loosely enough to be released where needed, and tight enough to survive the trip from lungs to tissues. That reversible binding is a simple physical rule scaled to a life-sustaining task. Breathing is a clear example of chemistry turned into function. Air reaches the small sacs of the lungs. Oxygen crosses into the blood and meets hemoglobin inside red blood cells. The blood carries it to cells, where mitochondria use oxygen to break down sugars and capture energy as ATP, the cell's usable energy currency. Carbon dioxide formed in this process diffuses back into the blood, travels to the lungs, and is exhaled. The cycle repeats with each breath. The atoms move by diffusion and binding, following gradients and affinities, no different in principle from reactions measured in a lab. On a planet-wide scale, oxygen also shapes landscapes. It reacts with metals to form rust. It helps turn rock into soil through weathering. It feeds fires that convert stored chemical energy into heat and light. Blue skies exist because molecules in the air scatter shorter wavelengths of sunlight. Oxygen is part of that mix. The colors at sunrise and sunset depend on how light passes through long paths in an atmosphere rich in oxygen-containing molecules and aerosols. The point is not romance. It is a chain of small interactions that add up to familiar scenes. Free oxygen is reactive, so it does not last in an atmosphere unless something keeps making it. That is why oxygen is a strong target in the search for life on exoplanets. Telescopes can split a planet's light into a spectrum and look for the fingerprints of certain gases. A sustained signal of oxygen, especially along with methane, would be hard to explain without continuous sources. On Earth, photosynthesis fills that role. If we find a similar pattern elsewhere, it would be a serious clue, not proof, that biology is at work. The link between cosmic origin and daily use is direct. Oxygen made in stars spreads through a galaxy, becomes part of new systems, then cycles through water, rocks, air, and organisms. Carbon made in stars does the same, forming the backbone of molecules in cells and the carbonates in stone. The periodic table captures these roles. Carbon sits in a group with silicon and germanium, but its bonding in water and at Earth-like temperatures is far more versatile. Oxygen sits with sulfur and selenium, sharing traits that show up both in minerals and in biochemistry. Placement on the table reflects electron structure. That structure sets chemistry. Chemistry sets what is possible in planets and in life. The fine details matter. The triple alpha path depends on a fleeting beryllium-8 and on a specific energy level in carbon-1,2. Helium capture reactions depend on core temperatures reached only after hydrogen is gone from the center. Yields of carbon and oxygen depend on a star's mass, how it mixes, and how quickly it loses mass in winds. Supernovae set how much of those elements escape and where they end up. Neutron-star mergers add heavy elements that life uses in trace amounts. Put together, these processes build the ingredient list that planets inherit. On Earth, the carbon cycle and the oxygen cycle are tied. Photosynthesis joins them by taking carbon dioxide and releasing oxygen. Respiration and decay join them by using oxygen and releasing carbon dioxide. Ocean chemistry links them by dissolving gases and forming carbonates. Rock weathering and volcanism link them over longer periods. Feedbacks in these loops help keep temperatures and ocean pH within ranges that allow liquid water and active biochemistry. When we change the amount of carbon dioxide in the air, we push on those feedbacks. The physics and chemistry do not change their rules. The system finds a new balance that reflects the new inputs. Seen together, carbon and oxygen explain how stars move from fusion to function. Fusion in a hot core builds carbon. Helium capture adds oxygen. Stellar winds and explosions deliver both to space. Planet formation traps them in solids and ices. Surface and interior processes move them between reservoirs. Biology, once it appears, uses them to store information, build structures, and release energy. The same two elements then cycle through air and water and rock, powering metabolism and shaping climate. None of this requires special pleading. It follows from nuclear structure, gravity, bond strengths, and the way energy flows from hot to cold. You can test this picture with observations. Spectra of old, metal-poor stars show lower carbon and oxygen than young, metal-rich stars. Supernova remnants contain strong lines from oxygen and carbon-bearing molecules in their cooling gas. Meteorites record the isotopic fingerprints of stellar processes in tiny mineral grains that predate the solar system. Ice cores on Earth record past changes in carbon dioxide and oxygen linked to climate and life. Modern instruments track seasonal swings in atmospheric carbon dioxide as plants grow and rest. Each piece matches the expectation that stars make the elements and that planets and life sort and cycle them. There is nothing accidental about carbon's 4 bonds or oxygen's 2. Those counts follow from electron shells. The shapes of molecules follow from how electrons arrange themselves to minimize energy. The stability of carbon-carbon and carbon-hydrogen bonds makes long chains and rings practical. The strong oxygen-hydrogen bond in water makes a stable solvent with a high heat capacity. These basic facts make it easier for complex chemistry to emerge and persist in environments like Earth's. The rules are simple. The outcomes look rich because there is time and space to explore many combinations. If you trace one breath and one bite of food backward, the path is clear. Oxygen in the breath formed in a star that ended long ago. Carbon in the food formed in another star, perhaps in a different part of the galaxy, and traveled a long route through gas and dust. Both reached Earth, joined into water, carbon dioxide, and organic molecules, and then entered a living cell. There, familiar reactions turned them into energy and structure. The periodic table is not a classroom poster. It is a field guide to those steps, showing which bonds can form and which reactions are likely. Carbon's strength is variety. Oxygen's is controlled reactivity. Together they build stable structures that can change when needed, and power systems that run in liquid water at ordinary temperatures. That pairing explains why forests grow, mussels work, rocks weather into soil, and a planet can hold both continents and oceans. The atoms are old, the cycles are steady, and the science is specific. Yet the supply of these elements depends on how stars live and where their work must stop. Iron sets that hard stop. In massive stars, fusion climbs in steps: hydrogen to helium, helium to carbon and oxygen, then to neon, magnesium, silicon, and nearby elements. Each step releases energy that pushes outward and balances gravity's inward pull. The balance holds only while fusion pays back more energy than it costs. At iron, the binding energy curve peaks. Fusing iron does not release energy, it absorbs it. When an iron-rich core forms, the outward push fades, gravity takes over, and the star's next chapter begins. Binding energy is the key idea. When light nuclei fuse, the average binding energy per nucleon increases, and the extra energy leaves as heat and light. The curve rises up to iron and nickel. Beyond that peak, fusion would lower the binding energy and need an input of power. A star cannot supply that. Hydrogen and helium fusion support stars for long stretches. Silicon burning runs for days in the most massive stars. Iron burning in a core is not a power source at all. Once iron piles up, the core has no way to resist further compression. Collapse begins fast. Photons at extreme energies break heavy nuclei into alpha particles and free nucleons, a process called photodisintegration. Electrons are driven into protons, forming neutrons and neutrinos. This is electron capture. Both processes remove pressure support. In less than a second, the core shrinks to a neutron-dense sphere only tens of kilometers wide. A teaspoon of that matter would outweigh mountains. The infalling layers crash onto the new neutron core. A shock forms, and at first, it stalls. Neutrinos, made in huge numbers, stream out. A fraction deposit energy behind the shock. Convection and fluid instabilities help. The shock revives, and the star explodes. This is a core collapse supernova. An explosion like this ends one star and seeds many others. Elements built during the star's long life are thrown into space. In the neutron-rich outflow, rapid neutron capture the R process builds nuclei heavier than iron, iodine, xenon, hafnium, gold, uranium, and more. The ejecta expand, cool, and mix into the interstellar medium. Shock waves sweep up nearby gas, compressing some regions, stirring others, and changing where new stars will form. The compact core left behind remains as a neutron star, or, if the mass is high, a black hole. Iron's role reaches from space into daily life. Earth's deep interior is iron-rich. As the planet cooled, heavy materials sank, forming a solid inner core and liquid outer core. Motion in the liquid outer core generates the geodynamo, which creates Earth's magnetic field. That field guides compass needles, shapes auroras, and helps protect the atmosphere from charged particles. Near the surface, iron oxides color rocks and soils. Iron forms strong alloys with carbon to make steel. In your blood, iron atoms sit at the center of heme groups in hemoglobin. Each heme binds oxygen in the lungs and releases it in tissues. The same element that ends fusion in a star carries oxygen to your cells. The chain from a dying star to a planet is long but direct. A massive star builds an iron core, collapses, and explodes. Its iron and other elements drift for millions of years, join a cold cloud, and become part of a rotating disk around a young Sunday. Dust grains stick and grow into planetesimals. Heat from impacts and radioactivity melts the largest bodies. Dense iron sinks to form cores. Lighter silicates build mantles and crusts. Water arrives and forms oceans. Over time, carbon and oxygen cycles begin at the surface. The iron that once marked a limit in a stellar heart becomes the working metal in a planet's engine and the active center in your bloodstream. Supernovae are rare on human timescales, but important on galactic ones. In a galaxy like the Milky Way, a core collapse supernova may occur once or twice per century. Each one injects energy and heavy elements into its surroundings. Over millions of years, many such events raise the average metallicity, all elements heavier than helium, of the gas. New generations of stars form from enriched material. Rocky planets become more likely as silicon, magnesium, and iron increase. Water becomes more common as oxygen increases. The galaxy's chemistry and structure evolve because massive stars end in explosions. Not all supernovae share the same origin. Core collapse events come from massive stars that run out of fuel at the core. Thermonuclear supernovae type Ia begin with a white dwarf in a close binary. The white dwarf gains mass from a companion star or merges with another white dwarf. Near a critical mass, carbon fusion ignites throughout the star. The runaway unbinds the white dwarf in seconds. No compact core remains. The star is completely disrupted. Type Ia explosions make large amounts of iron group elements and spread them widely. Because many have similar peak brightness after corrections, they are used to measure cosmic distances and to study the expansion of the universe. Chemically, they are major sources of iron and nickel in galaxies. Light from supernovae is a record of the physics inside. Early spectra show broad lines formed in fast ejecta. As the remnant ages and thins, forbidden lines of oxygen, sulfur, and calcium stand out. X-ray telescopes observe shock-heated gas. Radio telescopes see electrons spiraling in magnetic fields. Gamma-ray lines reveal short-lived isotopes such as cobalt-56 decaying to iron 56 inches thermonuclear explosions. Neutrino detections from the 1987 event in the Large Magellanic Cloud matched long-standing predictions for core collapse and confirmed that most energy leaves in neutrinos. Iron helps trace time in the Milky Way. Old stars in the halo have low iron relative to hydrogen. They formed before many supernovae had enriched the gas. Younger disk stars, like the Sun, show higher iron. Ratios such as oxygen to iron vary with age and location. Massive star explosions enrich oxygen quickly because massive stars die young. Type Ia supernovae enrich iron more slowly because binary systems take longer to reach runaway conditions. Mapping these ratios in many stars reveals the history of star formation and chemical mixing across the galaxy. Collapse outcomes depend on mass, rotation, and magnetic fields. If the collapsing core is modest, neutron degeneracy pressure supports a neutron star about 10-20 kilometers across. If the core is too massive, even neutron pressure fails. A black hole forms. Some collapses produce weak explosions with fallback, where part of the outer layers fall back onto the remnant. Others launch jets, powered by rotation and magnetic fields, driving narrow, energetic outflows. These differences create variation in light curves, spectra, and remnant shapes. Heavy element products from supernovae show up in many places. In cooling ejecta, atoms condense into dust grains. Some grains formed in ancient supernova outflows survived and were trapped in meteorites. Their isotopic ratios differ from solar system averages and match predicted yields from stellar burning and explosions. These pre-solar grains are physical samples of nucleosynthesis. In ocean sediments and lunar soil, scientists have found iron 60 radioactive with a half-life of about 2.6 million years, likely delivered by nearby supernovae in the recent geological past. Such finds link local space events to deposits on Earth. Type Ia supernovae add both iron and a tool for cosmology. Their light curves are powered by the decay of nickel 56 to cobalt 56 to iron 56. The rate of decline and the peak brightness correlate, allowing standardization. Surveys of distant Type Ia supernovae showed that the universe's expansion is accelerating. The cause is called dark energy. The same events that help weigh cosmic history also stock galaxies with iron group elements for future planets and stars. Iron also matters for planets beyond Earth. Planet density reveals composition. Mercury's high density points to a large iron core relative to its size. Mars likely has a smaller core. Its magnetic field faded early, changing how its atmosphere interacted with the solar wind. On Earth, changes in the magnetic field reflect changes in the flow of liquid iron. Those changes alter how cosmic rays reach the atmosphere and may leave chemical and isotopic fingerprints in rocks and ice. Iron's placement and motion inside a planet influence surface conditions over geologic time. In biology, iron's chemistry is both useful and risky. Iron can switch between oxidation states, which makes it valuable in enzymes that move electrons. Hemoglobin and myoglobin use iron to bind small molecules. Cells keep free iron low because it can catalyze reactions that damage tissues. Proteins store iron safely and release it when needed. Diet, transport, storage, and use form a controlled loop, the same kind of loop that operates at planetary scale with carbon and oxygen. Supernovae affect more than chemistry and light. Their shocks accelerate particles to near-light speeds, creating cosmic rays. These high-energy particles influence the chemistry of interstellar clouds and can create isotopes when they strike planetary atmospheres. Cosmic rays from supernova remnants help set the background radiation in a galaxy and add to the processes that shape new star-forming regions. The story is consistent across many kinds of data. Optical spectra list elements in ejecta, X-rays map hot plasmas in remnants, gamma rays trace radioactive decay, neutrino detections confirm core physics. Gravitational waves and kilonova light from neutron star mergers show where many R-process elements come from. Together, these measurements test models and set limits on how much of each element comes from each kind of event. The picture that emerges is steady. Massive stars build up to iron and then collapse. Thermonuclear runaways in white dwarfs add iron group elements. Neutron-rich events supply part of the heaviest elements. Winds and explosions spread material. Galaxies reuse it. Iron is not just a point on a chart. It is a boundary set by nuclear stability, the trigger for a star's collapse, a core metal in planets, and a working atom in blood. In massive stars, fusion builds until iron. Then gravity wins. The core falls, and an explosion follows. That supernova is more than a bright flash. It mixes, heats, and organizes matter for what comes next. Heavy elements disperse, enriched gas cools, new systems take shape. The same facts that stop fusion explain the iron in a bridge, the magnetic field of a planet, and the oxygen carried in a breath. Beyond that boundary lies a different path. Gold and platinum are rare because ordinary fusion cannot make them in bulk. Core fusion stops near iron. Further steps would cost energy. To move past iron, nuclei must grab neutrons faster than they can decay the rapid neutron capture path, or R process. It demands a flood of free neutrons and extreme energy. For years, core collapse supernovae were tested as the main site. They are powerful and common, and they spread elements widely. But models and stellar surveys showed gaps. The yields for the heaviest nuclei did not consistently match what we see in old stars and in meteorites. Attention turned to neutron stars. A neutron star is the compact remnant of a massive star's core. It is roughly 20 kilometers across, yet more massive than the Sunday. Matter inside is crushed into neutrons with a density we cannot reproduce on Earth. When two neutron stars orbit each other, they lose energy by radiating gravitational waves, ripples in space-time, and slowly spiral inward. In the final minutes, the orbit tightens, the stars distort, and then they collide. The merger throws out neutron-rich matter at high speed. In this ejecta, nuclei capture neutrons again and again in fractions of a second. As the hot debris expands and cools, the new, heavy nuclei decay towards stability and release light. The glow is called a kilonova. Its color and brightness change as the mix of elements changes. In 2017, detectors recorded gravitational waves from a neutron star merger, and telescopes across the spectrum watched the light. The data matched an R-process kilonova. It was the first direct, combined view of both the crash and the chemical products. The event showed that neutron star mergers can make large amounts of gold, platinum, and other heavy elements in a single burst. They are infrequent, perhaps. One event in a galaxy like the Milky Way every 100,000 years or so, but each one is rich. Over billions of years, a small number of mergers can seed many star-forming regions with heavy elements. Gold and platinum also stand out for how they behave. Gold does not rust or tarnish. It is soft enough to shape and stable enough to keep its shine. Platinum resists corrosion and stays strong at high temperature, which makes it useful in industry as well as art. Uranium and thorium, two more R-process products, are radioactive and decay slowly. Their decay releases heat inside rocky planets. On Earth, that heat helps keep the mantle mobile and supports plate tectonics over long spans of time. Even many rare earth elements used in electronics come, in part, from our process pathways. Devices we hold, clean energy systems we build, and signals we send all rely on atoms that likely formed in short, violent moments far from here. The path from a merger to a ring or a circuit is long. Heavy elements made in an outflow spread into the space between stars. That space, the interstellar medium, contains gas and dust grains. The gas is thin by human standards, only a few atoms in a cubic centimeter on average, but the volume is vast. Over time, gravity gathers gas and dust into clouds. Shock waves from supernovae compress some regions. Tides and stir from passing stars or from galaxy collisions twist and fold others. Cold, dense clouds, called molecular clouds, form. In these clouds, dust grains coated with simple ices help molecules assemble and help the gas cool. Cooling lets gravity pull harder than pressure resists. Dense pockets inside a cloud collapse and spin up. A young star forms at the center, fed by a disk of gas and dust. The disk is the workshop where solids grow. Tiny grains stick in gentle collisions, build pebbles, and then form larger bodies. Gravity takes over as objects grow. Planetesimals sweep up material and sometimes collide and merge. In the inner disk, rock and metal dominate. In the outer disk, ices are common. Over millions of years, a planetary system takes shape. Heavy elements from long past events end up in cores, mantles, crusts, and atmospheres. Stardust is not an idea. We can hold samples. Some meteorites contain grains that predate the solar system. Their isotopes do not match solar system averages. Instead, they match patterns expected from specific nuclear processes in red giant winds or supernova outflows. These presolar grains are tiny but direct. They are physical pieces of older stars captured in the rocks that fell to Earth. We also see live traces of recent events. Layers in ocean sediments and lunar soil contain atoms of iron 60, a radioactive isotope with a half-life of about 2.6 million years. That isotope likely arrived from one or more nearby supernovae within the last few million years, a reminder that our region of space is not static. As material moves, it stays mixed for a long time, but not forever. A cloud's chemistry reflects its past. Regions with many massive stars enrich quickly with oxygen, silicon, and magnesium, the products of core collapse supernovae. Over longer times, thermonuclear supernovae add iron group elements. Where neutron star mergers have occurred, the R-process imprint is stronger. Astronomers track these patterns by measuring element ratios in many stars. Old halo stars that formed early in the Milky Way tend to have little iron and, in some cases, unusually high R-process elements from one or a few early events. Young disk stars, like the Sun, carry a smoother blend. Dust and gas feed not only stars and planets, but also simple chemistry in space. On cold dust grains, hydrogen atoms combine to form H2. In slightly warmer regions, carbon and oxygen make CO. In denser, shielded pockets, more complex molecules form, some with carbon, nitrogen, and oxygen together. These are not life, but they are useful raw materials. They coat grains, ride into disks, and can later be delivered to young planets by comets and asteroids. The hydrogen in water on Earth is as old as the Big Bang. The oxygen was made in stars. The delivery routes vary, but the link back to earlier stars remains. When a star like the Sun ages, it swells and sheds its outer layers. The exposed core emits ultraviolet light that makes the expanding shell glow. We call these shells planetary nebulae. They are rich in carbon and nitrogen made during the star's giant phases. In more massive stars, the end is faster and louder. The core collapses, a supernova follows, and a shock wave sweeps through the surroundings. Both paths return matter to the interstellar medium. Both paths feed the next round of star formation. Neither is wasteful. The galaxy reuses almost everything. Heavy elements influence how disks evolve. Metals, astronomers' word for all elements heavier than helium, allow gas to cool more efficiently because atoms and dust radiate heat away. Cooling shapes how quickly a cloud can fragment and how massive new stars will be. Dust sets the opacity, which affects how light moves and how gas heats. In disks, dust controls how fast solids grow and how likely they are to drift inward. The mix of elements, grain sizes, and gas motions sets what kinds of planets can form and where. Giant planets form more easily in massive, cold outer disks. Rocky planets build where solids are dense and gas clears on the right schedule. Earth's resources bear signatures of those early steps. Gold and platinum are concentrated by geologic processes, but their global inventory is set by what the solar system started with. Some of the noble metals sank into Earth's core during early melting. Some were added later by impacts that delivered a late veneer to the crust and mantle. The patterns we mine result from deep, slow processes, magmas rising, water moving through rock, plates diving and lifting, that work with the starting chemistry supplied by ancient stars. The journey from dust to life adds another set of cycles. On Earth, carbon and oxygen move through air, water, soil, and living things. The carbon cycle links photosynthesis, respiration, weathering, and volcanism. The oxygen cycle links biology and rock chemistry. Trace amounts of heavy elements from our process events play roles in enzymes and in the behavior of proteins. These roles are not mystical. They follow from electron shells and bond strengths. An element's place in the periodic table sets what bonds it can form. Those bonds set how molecules act in water at Earth-like temperatures and pressures. Not all our process material comes from the same source in all galaxies. In small dwarf galaxies, a single neutron star merger can dominate the heavy element inventory for a long time. In larger galaxies, the mix averages over many events. Observations of ultra-faint dwarf galaxies show stars with very high R-process element levels relative to iron, consistent with one early merger enriching the whole system. In the Milky Way, we see a range that records many sites and times. This variety helps test models for how often mergers happen and how much material they eject. Supernovae add their own clocks. Type Ia supernovae, which come from white dwarfs, produce iron group elements, and follow delay times linked to how long it takes binary systems to evolve. Core collapse supernovae happen on short timescales because massive stars live fast. By comparing oxygen to iron ratios in stars of different ages, astronomers infer when each type dominated enrichment. Our process patterns add a third timer. Together, these clocks trace the pace of star formation and the frequency of the key events that set a galaxy's chemistry. We also see the motion of dust today. Instruments on high mountaintops and on the seafloor collect micrometeorites, tiny grains that fall through the atmosphere each day. Spacecraft measure dust streams in the solar system, some linked to comets and some to collisions in the asteroid belt. Even within our neighborhood, material is still moving, still settling, still entering the long loops that run from space to planet and back to space again, when impacts eject material or when a star sheds mass. The numbers put scale on the story. A teaspoon of neutron star matter would weigh billions of tons. A single neutron star merger can produce amounts of gold and platinum far beyond anything humanity will ever mine. The average density of interstellar gas is lower than the best vacuum we can make in a lab. Yet the total mass in a typical giant molecular cloud can be 1,000,000 times the Sun's mass. A protoplanetary disk may persist for a few million years. The cooling of a planet's interior takes billions. Time and scale are large, but the steps are specific. Every link in this chain is testable. Gravitational wave detectors hear mergers. Optical and infrared telescopes see kilonova light curves and spectra that carry the fingerprints of heavy elements. Gamma-ray and X-ray observatories watch supernova remnants and measure hot plasmas and radioactive decay. Meteorite labs count isotopes in pre-solar grains. Geochemists find live radioisotopes in Earth and Moon samples that point to nearby explosions in the recent past. Sky surveys map element ratios in hundreds of thousands of stars. The pieces fit. Heavy elements need extreme neutron-rich settings. Those settings exist. Their products match what we measure in space, in rocks, and in living matter. The same path that explains gold in a ring explains heat in Earth's mantle and rare atoms in your bloodstream. The same physics that stops fusion at iron points to the few events that reach beyond. The same gravity that builds a star, collapses a cloud, and piles dust into a disk. The rules are steady. Hydrogen and helium came first. Stars made carbon, oxygen, silicon, and iron. Mergers and some supernovae made much of the rest. Winds and explosions spread the results. Gravity gathered them again. Disks turned them into planets. Planets cycled them through rock, air, ocean, and life. The metal that does not tarnish, the element that powers a reactor, the trace atom in an enzyme, and the grain that fell from space onto a polar snowfield all follow from those linked steps. 4.5 billion years ago, Earth began as a spinning disk of gas and dust around a young Sunday. The ingredients were old. They came from earlier stars that lived, died, and threw their matter back into space. Nothing in Earth is brand new. It is a mixture of hand-me-downs, iron from massive stars, silicon and oxygen from stellar fusion, carbon and nitrogen from aging giants, and traces of heavier elements from supernovae and neutron star mergers. Gravity gathered these pieces into clumps. Collisions heated them, and a growing protoplanet took shape. Heat from impacts and from radioactive decay melted much of the young world. In a molten state, heavy elements sank, while lighter ones rose. Separation by density, called differentiation, set Earth's basic layers. At the center, iron and nickel pool to form the core. The inner part is solid under immense pressure. The outer part is liquid and in motion. Moving metal conducts electricity. Moving electricity creates a magnetic field. The geodynamo in the liquid outer core powers Earth's magnetic field, which steers charged particles from the sun, shapes auroras, and helps protect the upper atmosphere from slow erosion. Without this shield, gases important to climate could be stripped more easily. The core also stores part of Earth's heat and feeds slow convection in the mantle above. The mantle, made mostly of silicate minerals, rich in oxygen, silicon, magnesium, and iron, is solid on short times, but flows slowly over millions of years. Convection in the mantle drives plate tectonics. Plates move, collide, pull apart, and slide past each other. Mountain ranges rise, ocean basins open and close. Volcanoes release gases from the interior. Subduction drags surface material downward, mixing crust with mantle. This constant recycling regulates the long-term carbon cycle and keeps the surface chemically active instead of locked in place. The crust formed as the hottest early rock cooled and crystallized. Oceanic crust is thin and dense, made mainly of basalt. Continental crust is thicker and lighter, rich in granites and related rocks. Minerals in these rocks record cooling histories, water content, and past temperatures and pressures. A piece of granite is a cooled solution of silicate melts, crystallized in place and later lifted by tectonics. A beach of sand is mostly quartz and feldspar grains, ground from older rocks and carried by water and wind. Even common stones are the condensed dust of stars, reworked by heat, pressure, and erosion. Early Earth's air was not like today's. Volcanic gases likely supplied water vapor, carbon dioxide, nitrogen, and small amounts of other gases such as sulfur compounds. Oxygen gas was scarce because it reacts readily and was locked into minerals. Over time, life changed the air. Microbes evolved oxygenic photosynthesis, using light to split water and releasing oxygen as a byproduct. At first, that oxygen combined with dissolved iron in the oceans, forming iron oxides that settled to the seafloor. Only after these sinks filled did oxygen accumulate in the atmosphere. The rise in oxygen allowed more efficient energy use in cells and supported larger, more complex organisms. Nitrogen, now most of the air, is stable and inert under normal conditions. Its origin lies in both mantle outgassing and the recycled products of ancient stars. Water's path to the surface involved several steps. Hydrogen from the early universe and oxygen from stars combined as H2O wherever conditions allowed. Water existed as vapor in the hot inner nebula, as ice farther out, and bound in minerals in rocky grains. As Earth grew and heated, some water was released from minerals and volcanic gases. Impacts by water-bearing asteroids and comets likely added more. The final mix is still studied using isotopes of hydrogen and oxygen, but the result is plain. Oceans formed as the surface cooled, rain fell, and basins filled. Liquid water stabilized climate by storing heat and by dissolving and transporting ions that build minerals and buffer acidity. Water's properties help explain why it is central to habitability. It is an excellent solvent. Sugars, salts, and many gases dissolve in it, allowing chemical reactions to proceed and products to move. It has a high heat capacity. so it absorbs and releases heat slowly. This moderates climate, smoothing day-night and seasonal swings. It expands when it freezes because the solid forms an open crystal structure. Ice floats. Lakes and seas freeze from the top down, leaving liquid below where organisms can survive winter. Water's high surface tension and ability to wet minerals help it climb through soils and rocks, moving nutrients and shaping landscapes. These traits follow from the bent shape of H2O molecules and the hydrogen bonds they make with each other. On Earth, water cycles through reservoirs. It evaporates from oceans and lakes, condenses into clouds, falls as rain or snow, and returns through rivers and groundwater. Plants draw water from soil and release it back to the air. Subducting plates carry water down into the mantle, where it changes melting points and affects volcanism. Volcanic gases release water back to the surface. This loop runs on timescales from hours to millions of years. Carbon cycles tie in. Carbon dioxide dissolves in water, reacts with rocks, and forms carbonates. Weathering pulls CO2 from the air. Volcanism returns it. These feedbacks act as a thermostat, keeping temperatures in ranges that allow liquid water over long periods. Earth's inventory includes many trace elements with clear stellar origins and daily roles. Calcium, from helium burning in stars, builds bones and shells. Sodium and potassium, products of stellar fusion pathways, carry electrical signals in nerves and muscles. Phosphorus, key to DNA and energy molecules like ATP, links to past supernovae through nucleosynthesis chains. The presence of these elements on Earth reflects the mixture in the solar nebula. Their distribution today reflects geologic sorting and biological use. A major event in Earth's early history likely reshaped this distribution. A collision between the young Earth and a Mars-sized body, often called Theia, probably ejected material that later formed the Moon. Such an impact would have melted large parts of Earth, mixed the mantle, and affected how much volatile material remained near the surface. The Moon's formation changed tides and day length, which in turn influenced ocean mixing and climate cycles. Impacts large and small continued to deliver materials and to reset local crust. Each event was part of the same broad process, assembling and reworking a planet from inherited pieces. Earth's magnetic field, maintained by fluid motion in the liquid outer core, has flipped polarity many times. These reversals leave patterns in cooling lava flows and in seafloor basalts and help date spreading at mid-ocean ridges. The field's strength and shape vary as core flows change. These variations can affect how the solar wind couples to the magnetosphere and how auroras shift in latitude. The link from iron in a stellar core to iron in a planetary core to a moving magnetic shield is continuous and physical. Production, placement, motion, effect. The surface bears direct inputs from space even now. Dust from comets and asteroids falls through the atmosphere daily. Meteorites bring samples of early solar system materials, including tiny pre-solar grains. These grains carry isotopic patterns that match models of red giant winds and supernova outflows, providing a record older than Earth itself. In seafloor sediments and in lunar soils, scientists have found trace amounts of iron 60, a radioactive isotope with a half-life of about 2.6 million years, likely delivered by nearby supernovae in the recent geological past. These findings show that our neighborhood changes and that stellar processes still leave measurable marks. Water elsewhere adds perspective. Molecules of H2O are common in space. Telescopes detect water vapor in star-forming clouds, and in the atmospheres of some exoplanets. Icy moons like Europa and Enceladus hold subsurface oceans. Plumes vent water and salts into space, where spacecraft can sample them. Mars preserves signs of ancient rivers and lakes, and holds ice at its poles and in buried layers. Wherever hydrogen and oxygen are abundant and energy sources allow, water appears. This broad presence supports the use of "follow the water" as a guide in the search for life. Liquid water provides a medium where carbon-based chemistry can run at useful rates, and its presence hints at environments that stay within stable temperature and pressure ranges. On this planet, water shapes both nature and society. Rivers carve channels and carry silt that builds deltas. Glaciers grind valleys and leave moraines. Groundwater dissolves limestone and creates caves. Coasts change as waves and tides move sand. Civilizations cluster near reliable water, use it for irrigation and transport, and manage it with dams and canals. Energy use taps water in countless ways: cooling in power plants, reaction medium in industry, and direct motion in turbines. These uses rest on the same molecular traits that helped early chemistry on a young Earth. The view that Earth is an inheritance is practical, not poetic. Iron in the core came from stars that fused lighter elements, and from supernovae that scattered their products. Silicates in the mantle and crust reflect oxygen's abundance and silicon's bonding. Nitrogen, carbon, and oxygen in the air tie to both interiors and biology. Water binds hydrogen from the early universe to oxygen from stellar ashes. Radioactive elements such as uranium and thorium from our process events still release heat that keeps the mantle moving. Every layer and cycle reflects sources beyond our planet and processes within it. The balance that makes Earth habitable rests on feedbacks. Too little greenhouse gas and the surface freezes. Too much and it overheats. Weathering rates increase in warm, wet conditions, drawing down CO2. In cold, dry conditions, weathering slows, allowing CO2 to build from volcanic outgassing. Plate tectonics keeps this loop running by building mountains for weathering and by recycling carbonates through subduction. Life participates by accelerating weathering on land and by burying carbon in sediments. None of these loops erase the link to stellar inputs. They organize those inputs into a system that can persist. Simple definitions help anchor the story. A planetesimal is a building block tens to hundreds of kilometers across. Differentiation is separation by density in a molten or partially molten body. Outgassing is the release of gases from melting rock. Oxidation is a reaction where an element loses electrons. Iron rusts when it oxidizes with oxygen and water present. A solvent is a fluid that dissolves other substances. Water's polarity and hydrogen bonding make it effective. These terms describe steps and tools, not a script. The outcomes follow from initial composition, energy sources, and time. Earth's oceans cover most of the surface and store most near-surface water, but the entire system includes ice, groundwater, and water in minerals. Deep minerals can hold water in their structures. Subducted slabs carry these minerals downward. Rising magmas carry water back upward. This deep water cycle changes melting points, affects the style of volcanism, and can influence crust thickness. The ocean atmosphere system, meanwhile, exchanges water daily through evaporation and precipitation. Salts in the ocean come from weathering and from hydrothermal vents at spreading ridges. Their relative proportions have stayed similar over long times, another sign of steady, balancing flows. Different worlds show what Earth might be without certain pieces of its inheritance or processes. Venus is similar in size but lacks plate tectonics today and holds a thick CO2 atmosphere with crushing pressure and intense heat. Mars is smaller. It cooled faster, lost most of its magnetic field early, and its thin atmosphere holds little heat. Both examples remind us that starting mix, planet size, and internal motion matter. Earth's particular combination, a sizable iron core, active mantle, mobile plates, accessible water, and an atmosphere that life could modify, arises from linked steps rather than from chance alone or from design. Physics set the rules. Time explored the options. The materials that make daily life possible are part of the same chain. Copper, zinc, and nickel sit with iron in ores formed by fluids moving through crust or by magmas cooling and separating minerals. Phosphates form in marine settings and concentrate nutrients that once cycled through organisms. Silica makes glass. Clay minerals make bricks. The mobile electrons in iron and copper conduct electricity. The stable lattice in quartz resists heat. These properties follow from electron shells and crystal structures that reflect where each element sits on the periodic table positions set by the numbers of protons and electrons that stars and stellar remnants made. From the first dust grains that stuck together to the present web of cycles, the line is unbroken. Earth gathered what earlier stars produced, sorted it by density and chemistry, and kept it moving with heat from formation, from radioactivity, and from tides. Water carried heat and chemicals over the surface. Life added new loops and new sinks. The record sits in rocks, in ice, in seafloor sediments, in meteorites, and in today's measurements of gas, heat flow, and magnetic fields. The same atoms that formed in distant places now build continents, move through rivers, and circulate through cells. Every person carries a quiet record of the universe in their body. "We are made of stardust" is not a metaphor. The atoms in you were forged in stars, sent into space, and later built into living cells. Calcium strengthens bones. Iron moves oxygen in blood. Carbon forms the skeleton of complex molecules. Each atom is older than Earth and holds a clear origin in known physical processes. Begin with carbon, the framework of life. Carbon atoms make 4 strong bonds, so they build chains, rings, and branching shapes. That is why carbon forms DNA backbones, protein structures, sugars for energy, and fats for storage and membranes. Carbon in your cells exists because dying stars once fused 3 helium nuclei into 1 carbon nucleus in a reaction called the triple alpha process. Those atoms drifted in space, joined the cloud that formed the sun and planets, and later entered the food you eat and the tissues you grow. Think of oxygen next. When you inhale, oxygen crosses from tiny air sacs into blood, binds to hemoglobin, and reaches cells, where it helps release energy from sugars. Oxygen also sits in water, proteins, and DNA. It formed in stars when carbon nuclei captured helium at high temperature. When those stars ended, they released oxygen to space. Some of that oxygen became part of Earth's air and oceans. Some became part of you, combined with hydrogen as the water that moves through every tissue. Iron links human biology to violent events in space. In hemoglobin, an iron atom sits at the center of a heme group and holds oxygen for transport. Without iron, breathing would not deliver oxygen to cells. Iron is not a normal power source in stars. Fusion up to iron releases energy, but making iron in bulk in the core does not. Large amounts of iron are made and spread by supernova explosions when massive stars collapse and explode. The iron in your blood came from such an event and later joined Earth's materials. Calcium hardens bones and teeth. Stars in late stages make calcium by fusing lighter elements in hot shells, and supernovae spread it. On Earth, calcium cycles through rocks, shells, and soils, and in people it builds a strong frame. Phosphorus is rarer, but essential. It links DNA strands and stores energy in ATP, the molecule cells use to power work. Its production traces back to massive stars and supernovae. Without phosphorus, cells could not organize genetic material or move energy efficiently. Potassium and sodium set up electrical signals. Nerve cells pump sodium out and potassium in, then let them flow back through channels to fire a signal. Heartbeats, muscle movement, and thought rely on this fast exchange. Both elements formed in stars and reached Earth through the same chain as carbon, oxygen, calcium, and iron. Trace elements matter too. Zinc sits in many enzymes. Copper helps transport electrons and supports blood chemistry in several organisms. Iodine is needed for thyroid hormones. Magnesium is a helper in hundreds of reactions. These atoms came from a mix of stellar fusion and neutron-rich processes in supernovae and neutron star mergers. They are present in small amounts, but the systems they support are central. These parts fit life because of their basic chemistry. Carbon makes strong, flexible, covalent bonds. Oxygen reacts in controlled ways and can accept electrons in energy pathways. Iron binds gases reversibly. Calcium forms stable salts and can switch between hard storage and mobile forms. Phosphorus forms high-energy bonds that can be made and broken on demand. Potassium and sodium carry charge in water. Life did not create these properties. It used what physics and chemistry already allowed. This inheritance creates kinship across species and with Earth itself. The calcium in bone matches the calcium in a shell. The iron in blood matches iron in basalt and in Earth's core. Oxygen burns in flame, rusts metal, and supports breath for the same reason. It follows the same reaction rules in every setting. The idea is not to make us feel small or large. It is to describe the link between personal biology and natural processes that act on galactic scales. For a long time, humans did not know this link. People watched the stars for seasons and stories, but did not know their makeup. Early workers on matter were alchemists. Their goals mixed practical and mythical aims, turning base metals into gold, finding elixirs, but they tested, heated, mixed, and observed. The modern shift began when thinkers asked what elements are. In the 1600s, Robert Boyle argued that substances are built from simpler parts and that careful experiments can reveal them. In the late 1700s, Antoine Lavoisier measured masses before and after reactions, showed that matter is conserved, and listed elements based on repeatable tests. Chemistry gained a clear base, but it still applied only to Earth. The question remained, what are stars made of? The answer needed a way to read light. Spectroscopy provided it. Heat an element, and it emits or absorbs light at very specific colors. Split that light with a prism or grating, and you see lines or pattern unique to that element. Early in the 1800s, Joseph von Fraunhofer studied the sun's spectrum and mapped dark lines crossing it. Later, Gustav Kirchhoff and Robert Bunsen showed that each element produces bright lines at exact places, and those places line up with the sun's dark lines. Match the patterns, and you identify the element. The sun and stars contain the same elements known on Earth. The old idea of a special heavenly substance was not needed. Spectroscopy did more than confirm a list. In 1868, observers of a solar eclipse saw a spectral line that did not match any known element. They named the source helium after the Sunday. Years later, helium was found on Earth. This was the first time an element was discovered in the sky before being identified here. In the 1,920 seconds, Cecilia Payne analyzed many stellar spectra and showed that hydrogen is by far the most abundant element in stars, with helium second. Heavier elements are present, but in small amounts. Her result changed how we think about stars. They are mostly hydrogen and helium, not Earth-like materials stretched thin. Once we knew what stars hold, the next step was how elements form. In the 1,950 seconds, a group of researchers, often referred to by the initials B²FH, for Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, organized the paths. Light nuclei fuse in steady burning. Heavier nuclei form in shells in massive stars. Some isotopes build by slow neutron capture in aging stars. Others need rapid neutron capture in violent settings. Supernovae and neutron star mergers spread the results. This framework tied the periodic table to astrophysics and explained how the mix of elements in a galaxy changes over time. Modern tools extend the method. Telescopes split the light of distant stars and galaxies into spectra and read the element lines. Gravitational wave detectors register neutron star mergers. Optical and infrared observatories watch the glow of kilonovae and see the fingerprints of heavy elements forming. Gamma-ray and X-ray satellites study supernova remnants and detect radiation from short-lived isotopes. Laboratories measure isotopes in meteorites and find pre-solar grains, tiny crystals whose element and isotope ratios match the output of red giants and supernovae. Ocean sediments and lunar samples contain atoms of iron 60, a radioactive isotope likely delivered by nearby supernovae a few million years ago. All lines of evidence agree. The elements in living things and in rocks are the same elements made in stars and in their deaths. The periodic table is now both a chemical chart and a record of process. Hydrogen and helium fill the first row and reflect the early universe. Carbon, nitrogen, and oxygen mark common fusion products and the main parts of biochemistry. Silicon, magnesium, and iron show what massive stars and thermonuclear supernovae provide to build rocky planets. Gold, platinum, and uranium need neutron-rich bursts. Element positions reflect electron structure. That structure sets how atoms bond. Bonding sets mineral and biological behavior. The same chart guides a geologist, a biologist, and an astronomer. The way we learned these facts matters. The path runs from trial and error craft to careful measurement to reading light as a code. It shows that questions about distant things can be answered with nearby tests if we understand the link between cause and signal. A spectrum is a measurable pattern. The match between an observed line and a laboratory line is an objective result. When many independent checks, light, particles, rocks, point to the same story, confidence grows. Seen this way, a mirror is not only a surface, it is a map of element use. Carbon builds the structure of cells. Oxygen helps release energy. Iron carries that oxygen. Calcium stores strength. Phosphorus moves energy and links DNA. Sodium and potassium run signals. trace elements set enzymes to work. Each role uses properties set by electron shells and by nuclear paths that ran in other places and times. The line from a helium nucleus in a hot stellar core to a carbon atom in DNA is long, but each step is clear. For most of history, stars were lights at a distance. Now their light is also a record. It carries the same element fingerprints we see in the lab, the same structure that places atoms on the periodic table, and the same clues that reveal how old a star is and how it formed. The composition of the Sun can be read from a spectrum taken on Earth. The makeup of a distant galaxy can be read from light that left it when humans did not yet exist. These are not opinions. They are measurements anchored to physical rules. The human body and the night sky use the same parts for the same reasons. The atoms in a bone and in a meteor follow the same bonding rules. The iron that ends fusion in a star drives a heartbeat on Earth. The method that identified sodium in a flame identifies sodium in a star. The link is specific, testable, and complete enough to trace an atom's likely path, formed in a star, spread by an event, gathered in a cloud, built into a planet, cycled by geology and life, measured by light. The heavens and the earth speak the same language. Atoms built in stars, moved by gravity, and read by light. Matter is not wasted. It changes place and form, but it keeps going. This steady reuse is the universe's recycling system. It explains why galaxies keep making new stars, why planets grow from dust, and why living chemistry has the parts it needs. At first, the ingredients were few, mostly hydrogen and helium, with a trace of lithium. Gravity gathered them into the first stars. Fusion in those stars made new elements. When those stars aged and died, they returned enriched gas to space. New clouds formed, collapsed, and lit up again. With each cycle, the mix gained carbon, oxygen, silicon, iron, and more. Your atoms have passed through these loops perhaps many times before joining you. Galaxies are where this recycling is organized. Inside them, cold, dense regions called molecular clouds hold hydrogen molecules, carbon-bearing gases, and fine dust. Young stars form inside these clouds. Their light and winds carve hollows and create shock fronts. Those shocks can compress nearby gas and spark the next round of star birth. The process is not gentle in detail, but its results are steady. One generation shapes the next. Star lifetimes span huge ranges. Small stars burn fuel slowly and may live trillions of years. Massive stars burn fast and end in a few million years. No matter the track, stars give matter back. Low and mid-mass stars shed outer layers and make glowing shells called planetary nebulae. Their cores cool into white dwarfs. High-mass stars collapse and explode as supernovae, spreading heavy elements far and fast. Even the leftovers, white dwarfs, neutron stars, black holes, affect the gas around them by gravity, winds, or jets. Each round adds different items to the pantry. The first stars made carbon and oxygen. Later stars, born in enriched gas, pushed to silicon, sulfur, calcium, and iron. Explosions and, in some cases, neutron-rich events made part of the heavy end of the table. By the time the Sun formed, the local cloud had passed through many cycles. That is why Earth is not a helium balloon with stray dust, but a rocky world with water, continents, and a diverse chemistry. Recycling scales up to whole galaxies. Energy from massive stars and supernovae can drive gas out of star-forming regions and even out of a galaxy's disk. Some of that gas cools and falls back in a galactic fountain, feeding new clouds later. Galaxies also draw fresh gas from their surroundings. When galaxies interact or merge, their gas is stirred and squeezed, and star formation often surges. The future merger of the Milky Way and Andromeda will mix their gas and stars and make a new system with a fresh cycle of birth and return. None of this is waste. It is circulation. The link is personal. Oxygen in your lungs once sat in a star. Calcium in your bones drifted as dust before joining rock and then life. Iron in your blood formed in a core collapse and rode an expanding wave into space. Even the finest grains between stars matter. Dust particles, often silicates, and carbon carry ices of water, ammonia, and carbon monoxide. They stick in gentle collisions and grow into pebbles and larger aggregates. Over time, these solids become planetesimals, the seeds of planets. What looks like dirt is the start of worlds. Recycling includes both force and finesse. Supernovae tear stars apart, but their debris cools into thin threads and clumps that seed the next generation. Black holes pull matter inward, but their outflows can heat gas and set the pace of star formation across large regions. Collisions scatter, but they also mix. The result is a system that keeps changing, yet keeps producing the conditions for stars and planets to form. Life depends on this loop. Without repeated cycles, there would be little carbon for organic molecules, little oxygen for water and breath, little phosphorus for DNA, little iron for blood. Water on Earth likely arrived by more than one path, bound in minerals, released by volcanoes, and delivered by icy bodies. Every path traces back to the same source, elements made in stars and returned to space, then gathered again by gravity and time. We live in an era where this process runs at a steady rate. Enough cycles have enriched the gas to make rocky planets common, yet there is still plenty of raw material to build new stars. Far in the future, as gas is used and not fully replaced, star formation will slow. For now, the system breathes. Matter leaves stars, cools, gathers, and lights up again. The atoms that once burned in a core can now shine in a crystal, roll in a river, or pulse in a wrist. Nothing is truly lost. It is reassigned. The sky you see is a snapshot inside this motion. Bright stars mark current engines. Dark lanes mark dust that will form something new. Nebulae glow where ultraviolet light hits gas enriched by past lives. The Milky Way is not a band of fixed lights. It is an ecosystem. Gas flows in and out. Stars are born, age, and return material. Dust forms, grows, and builds solids. You are not outside this. You are made from it and live within it. Time has its own language in this story. Atoms carry clocks. Some versions of elements, radioactive isotopes, are unstable and decay into stable forms at fixed rates. The time it takes for half of a sample to decay is the half-life. That stability makes these isotopes natural timers. They tick in rocks, in meteorites, in old stars, and even in you. Because the rates are fixed for each isotope and do not depend on where they sit, we can use them to date events across a vast range. Carbon-14 is a familiar short-term clock. High-energy particles from space hit nitrogen in the atmosphere and make carbon-14. Plants take it in as CO2. Animals eat the plants. While alive, Organisms keep the same ratio of carbon-14 to carbon-12 as the air. When life ends, intake stops, and carbon-14 decays back to nitrogen at a known rate. By measuring what remains, we can date organic remains up to about 50,000 years. This tool has set timelines in archaeology and recent geology. For deeper time, we use isotopes with longer half-lives. Uranium-238 decays to lead-206 with a half-life of about 4.47 billion years. Uranium-235 decays to lead-207 with a half-life of about 704 million years. Thorium-232 decays to lead-208 with a half-life of about 14 billion years. Potassium-40 decays to argon-40 inches, 1.25 billion years. Rubidium-7 decays to strontium-80, 7 inches, 49 billion years. Each pair offers a different clock speed. When minerals crystallize, some include parent isotopes and exclude daughter isotopes. Over time, parents decay and daughters accumulate. By measuring parent-to-daughter ratios and knowing the decay rates, we can calculate ages. Zircon crystals are especially useful. They hold uranium but little lead when they form, and they resist later change. The oldest zircons on Earth are about 4.4 billion years old, and uranium lead dating of many samples places Earth's formation at about 4.54 billion years. Meteorites' unchanged fragments from the early solar system give the same age. With other isotope systems, geologists date lava flows, mountain building, and the cooling of rocks buried deep and later lifted. Each method is a check on the others. When several agree, the timeline is firm. These clocks run in stars too. Old, metal-poor stars in the halo sometimes show lines of thorium and uranium in their spectra. By comparing the present amounts of those isotopes to stable neighbors made by the same R process, astronomers estimate how long decay has been running. The results, often 12-13 billion years, fit with ages of the oldest star clusters and with the age of the universe. Freshly made isotopes also light up events. In a thermonuclear supernova, nickel-56 decays to cobalt-56 and then to iron-56. The heat from those decays powers the light curve as the explosion fades. Matching the decline of light to the decay rates reveals how much of those isotopes were made and how the ejecta expand. Radioactive clocks record planetary processes as well. Samarium-neodymium and rubidium-strontium systems trace how Earth's crust separated from the mantle. Lutetium-hafnium in zircon captures the timing of early crust growth. Potassium-argon marks the cooling of volcanic rocks and the timing of eruptions. These tools piece together not only when events happened, but how Earth's chemistry changed through time. The largest clock comes from the sky itself. The faint microwave glow that fills space. The cosmic microwave background carries patterns set when the universe was very young. Combined with measurements of the expansion today, those patterns imply an age of roughly 13.8 billion years. This figure is checked against the ages of the oldest stars and clusters, and against the history we read with radioactive isotopes. The numbers agree within their uncertainties, showing that the clock's atomic and cosmic are in step. Radioactive decay is not concerned with us. It runs at the same pace in a cave, in a crystal, or in a cloud. That indifference gives it power as a measure. It shows that time is recorded in matter. It also reaches into daily life. Potassium 40 inches, your body decays slowly. It is a tiny part of natural background radiation. Smoke detectors use americium-241. Medical scans use traces that decay with short half-lives. These are not distant ideas. They are the same physics that dates rocks and lights supernovae. Put recycling and clocks together, and the picture is complete. Atoms move between stars, gas, dust, planets, and life. Along the way, some carry timers. We can read those timers to learn when a rock cooled, when a star exploded, when a planet formed, and how long a galaxy has been building its metal content. We can tie the age of a river delta to the time since a volcano erupted upstream, and both to the global cycles that regulate climate. We can match the glow of a supernova to the mass of radioactive nickel it made. These are practical links between events and signals, not guesses. Nothing in this chain requires special pleading. Hydrogen and helium came first. Fusion in stars built many heavier elements. Explosions and mergers made part of the rest. Winds and shocks spread them. Gravity gathered them again. Disks turned dust into planets. On at least one of those planets, water and carbon chemistry used the common properties of a few elements to build cells. Radioactive isotopes marked the passing of time all along. The galaxy today is busy because the loop continues. The light from a star, the sand in a river, the air in a lung, and the date written in a crystal are all parts of the same system, running on simple rules over long spans. Before there were labs or telescopes, people still wanted to know what the world was made of. Sky, sea, soil, flame. Each asked for an explanation. Without modern tools, cultures built frameworks from what they could observe. They shaped stories where fire, air, water, and earth were not just materials but guiding forces. These early models were simple, but they reached for the same goal science reaches for now: a small set of ingredients and rules that can explain many different things. Fire stood out first. It moved, it consumed, it lit the night. To early thinkers, it looked alive. Greek philosophers placed it among the basic elements. Some, like Heraclitus, tied fire to change itself, seeing the world as a steady exchange of burning and cooling. In Persian tradition, flames symbolized truth and purity and were kept as sacred. Across myths, fire arrived as a gift or a theft, useful, dangerous, never ordinary. Without chemistry, it made sense to treat fire as fundamental. Heat and light were basic to survival. Water earned a similar status. It grew crops, carried fish, and carved land. But it could also flood and destroy. Civilizations tracked river cycles and built calendars around them. Ancient stories pictured cosmic waters as the source of creation, a vast reservoir from which the world rose. To make water a primary element was a way to explain why life clusters where water flows and why whole regions depend on seasonal rain. Air seemed invisible, yet necessary. It filled lungs and pushed sails. Many languages tied breath to spirit. The idea that a subtle, moving substance linked living things together was reasonable long before people knew about oxygen or nitrogen. To treat air as an element was to name something you could not see but could feel every time you inhaled. Earth felt solid and reliable. It offered food, ore, and shelter. People personified it as a mother because it supported life and kept its shape. If you build your world from daily experience, Earth naturally becomes a basic category. Rocks and soils were the base layer of everything familiar. These four ideas, fire, water, air, Earth formed systems that tried to unify experience. Empedocles in Greece described how they combined and separated. In China, a five-phase model wood, fire, earth, metal, water-linked material change with music, medicine, and politics. Such systems were not precise physics, but they did aim at a kind of order. They said, many things can be traced back to a few patterns. Over time, a different approach took hold. Some philosophers proposed atoms, tiny, indivisible building blocks, as the base of matter. Alchemists experimented with metals and heat, learned from failures, and passed down techniques. Measurement changed everything. In the 1600s and 1700s, careful weighing before and after reactions showed that mass is conserved. Lists of real elements grew. Fire became a process, not a substance. Air became a mixture of gases. Water became a molecule. Earth split into minerals and metals with distinct behaviors. Science then turned outward. If matter on Earth has certain elements, what about the sun and the stars? The answer came from light. Heated elements emit and absorb specific colors. A prism spreads those colors into lines that are unique to each element. When astronomers compared solar lines to lines measured in laboratories, they matched. The sun contains the same elements we know here. Helium was first seen in the sun and only later found on Earth. Further studies showed stars are mostly hydrogen and helium. The periodic table stopped being a purely terrestrial catalogue and became a universal one. From there, the story of elements moved into the hearts of stars. Fusion explained how hydrogen becomes helium, how helium becomes carbon and oxygen, and how massive stars build up to silicon and iron. Supernovae and neutron star mergers explained part of the heavy end: gold, platinum, uranium. The classical elements were not wrong in intention. They were early attempts to group experience. The modern set is more detailed and more predictive. It tells us why water dissolves salts, why iron rusts, why rocks are strong, and why air supports fire and breath. Culture did not disappear when science grew. The language remains. We still say grounded, air of confidence, ideas catch fire, or emotional flood. These phrases echo older frameworks and point toward patterns that science later quantified. You can hold both views at once: respect for early efforts to find unity and clarity from measurements that show how atoms, bonds, and reactions actually work. Seen through this lens, the world is not divided into earthly and heavenly matter. It is one set of atoms in many arrangements. Fire is rapid oxidation. Water is H2O formed from hydrogen in the early universe and oxygen from stars. Air is mostly nitrogen and oxygen, with traces of argon and carbon dioxide. Rocks are silicates and oxides, built from silicon, oxygen, aluminum, iron, magnesium, and other elements. The same rules apply in a candle flame and in a star, adjusted for temperature, density, and scale. A short thought experiment makes the role of stars clear. Imagine a universe in which stars never form. Hydrogen and helium would still spread out after the Big Bang. Gravity would still pull, but without fusion. Dense clumps would not shine or balance their collapse with heat. They would fall inward, stay cold at the edges, and make little structure that radiates. The periodic table would stop near the beginning. Hydrogen, helium, a trace of lithium. No carbon, no oxygen, no nitrogen, no silicon, no iron. Chemistry would be thin. No rocky planets, because there would be no rocks to make. No water, because oxygen would not exist. No biology, because the elements it needs would be missing. Galaxies would lack bright spirals and glowing clouds. The sky would not have constellations because there would be no points of light. The glow left from the Big Bang would remain the dominant light and would fade slowly with expansion. Time would tick, but it would be hard to mark because there would be no stellar lifetimes or supernova flashes to divide one era from another. Black holes might still form from rare direct collapses of gas, but without stars and dense disks to feed them, they would be quiet. The universe would expand, cool, and stay simple. Our universe is not like that because gas did gather and light up. Stars formed. They cooked heavier elements and returned them to space. Disks around young stars built planets from dust and ice. On at least one planet, water and carbon chemistry ran steadily enough for life to appear. None of this happens without stars. They are the engines that turn a thin, uniform start into a complex, structured present. Stars also set the tempo. Small red stars burn slowly and will outlive every galaxy we see today. Massive blue stars burn fast and die young. Supernovae send shock waves through gas and shape where and when new stars form. Neutron star mergers are rare, but supply part of the heaviest elements. These processes create variety in what planets can be made and in what surface conditions are possible. They also spread the elements needed for air, rock, and life. The connection to human experience runs through ordinary things. The warmth from a stove is controlled oxidation, the same type of reaction, in principle, that powers a flame or helps cells release energy. Glass is melted silica, made from silicon, and oxygen produced in stars. Concrete binds calcium-bearing minerals. Calcium is made in late-stage stars. Steel relies on iron. Iron is abundant because of how supernovae and thermonuclear explosions distribute iron group elements. Salt dissolves in water because of electrical charges on ions and the polarity of water. These properties follow from electron shells set by atomic number. The same logic organizes the sky. Spectra split starlight into lines that mark hydrogen, helium, calcium, sodium, iron, and more. Those lines reveal surface temperatures and compositions. They also show motions through Doppler shifts. The light curve of a supernova declines with a rate tied to radioactive decay of nickel and cobalt. Gravitational wave signals trace in spiraling compact objects and match neutron star masses. Each measurement adds a piece. Combined, they tell a consistent story. Atoms come from stars, move through space, and build new systems. The idea of recycling anchors the big picture. Gas cools and collects. Stars form and change the gas. Dying stars return enriched material. Dust grains grow and seed planets. Planets cycle water, carbon, and other elements between air, ocean, rock, and life. Some gases leak to space. Some water and rock return to the interior by subduction. Over millions to billions of years, these loops make a surface that can support steady chemistry. Radioactive clocks let us set dates inside that flow. Carbon-14 dates recent life and artifacts. Uranium-lead, potassium-argon, and other systems date rocks and volcanic eruptions. Thorium and uranium in old stars estimate ages near the universe's beginning. The cosmic microwave background sets the overall age. These independent clocks agree, making a timeline that runs from the first light to now, with enough detail to place key events. In that timeline, the myths of elements find a new place. Fire is no longer a root substance. It is a reaction that shows how oxygen and fuel interact. Water is not a primary element. It is a molecule whose properties make life's chemistry mobile and stable. Air is a mixture that breathes because oxygen can bind and release in blood, and because nitrogen's stability provides a safe background. Earth is not one thing. It is many minerals and metals bound by gravity and heat. The old categories captured features that mattered. The modern ones explain why those features appear. Science and culture do not have to compete. Cultural stories build meaning from observation. Science builds models from tests and measures. Both seek coherence. Both say the world is connected across scales and times. The classical elements are useful metaphors. The periodic table and stellar nucleosynthesis are useful explanations. You can still use the language of fire, air, water, and earth to talk about health, emotion, or craft, while using carbon, oxygen, silicon, and iron to design materials and trace origins. The starless universe thought experiment brings the point home. Without stars, there is no path from simple to complex. With stars, the path opens. Hydrogen to helium, helium to carbon and oxygen, up to silicon and iron, enriched gas to disks, disks to planets, water and carbon chemistry to cells. The difference is not small. It is the difference between a thin fog and a world with rivers, soil, and mines. The steps are physical and repeatable. Gravity collects, fusion runs, winds and explosions return material, and gravity collects again. So when you light a fire, drink water, breathe, or place a hand on rock, you can name each step in modern terms and still recognize the older pattern: heat and light from reactions, a solvent built from common elements, a moving, invisible mixture that supports life, a solid built from silicates and oxides. Underneath both languages lies the same system: atoms from stars, moving through cycles, following rules that hold from a laboratory flame to a galaxy. Stars make the universe active. They build the elements, shape galaxies, set clocks, and enable worlds. Take them away, and the story stops early. Leave them in, and the story gains structure. Periodic tables, spectra, planets, oceans, and living networks that can ask and answer. The continuity from ancient guesses to modern measurements is not a straight line, but the aim is the same. Find the few simple rules that explain the many. In our era, those rules are clear enough to describe why the sky shines, why the ground is solid, why water flows, and why breath works. The language has changed. The search for unity has not. The universe around us feels busy. Stars shine in every direction. Nebulae glow where new stars form. Supernovae throw fresh elements into space. It can seem like this is how things will always be. But we live in a special season. Star making has a timeline. Element making has a timeline. We are in the middle, when both are still active and visible. About 10 billion years ago, galaxies made stars at their fastest rate. Gas was thick in their disks. The first large generations of stars enriched that gas with carbon, oxygen, silicon, and iron. Since then, the fuel has been used and spread out. Star formation has slowed. It will keep slowing as galaxies consume the gas they have and lose some to winds and to the growing distance between systems. New stars will still form for a long time, but fewer each era. The cosmic factories will dim. When fewer stars form, fewer new elements are made. Heavy elements do not appear on their own. They are forged inside stars, in supernovae, and in rare neutron star mergers. As the supply of fresh stars declines, the production line thins. The elements already out in space will last. They will cycle through dust, rocks, and planetary crusts. But the rate of first-time creation will fall. The periodic table will stay the same, yet the universe will stop adding to its stock. Existing stars will follow their paths. Massive stars will still burn fast and die as supernovae, scattering calcium, iron, and other elements one last time. Medium stars like the Sun will expand into red giants, shed their outer layers, and leave white dwarfs hot, dense cores that cool slowly. Small red dwarfs will persist far longer. They sip their hydrogen. They can glow for trillions of years. In the deep future, they will be the last visible stars, faint embers in wide darkness. After that, even they will fade. Picture that distant sky. Fewer points of light, more remnants. White dwarfs cooled to dark, black dwarfs. Neutron stars still heavy and small, slowly losing energy. Black holes quiet and dominant by mass. Supernovae rare, perhaps one across vast volumes in very long stretches of time, with few explosions to stir gas and few newborn stars to shine. The cycle of matter slows. The universe does not freeze, but the visible drama eases. If cosmic expansion keeps accelerating, each galaxy will become an island. The gap between islands will grow. Light from one will no longer reach another. Within each island, the supply of gas will be fixed and will decline. New stars will be born only from what remains. Eventually, the kitchens cool. The chemistry does not vanish, but its inputs stop growing. The abundance of elements becomes a record rather than a work in progress. On very long timescales, stranger steps may occur. Collisions between remnants could spark brief fusion. White dwarfs in close pairs could merge and flare. If protons decay over unimaginable spans, matter itself would slowly fade. These ideas are still speculative. What we can say is simpler and enough for our horizon. The main era of forging elements in stars and scattering them widely will end. Creation will give way to circulation. For us, this is both a limit and a gift. We live when galaxies still build stars and planets. We live when the night sky carries light made minutes ago by the sun, and light made millions of years ago by distant stars. Our environment holds water, rock, air, and a web of life, because past stars ran their cycles and returned their products to space. We are late enough that many elements exist, early enough that new stars still form. A fortunate middle. In that middle, elements act as memory. Carbon tells of the triple alpha steps in a hot core. Oxygen recalls helium capture in massive stars. Iron marks collapse and explosion. Gold and platinum point to neutron-rich mergers that shook space-time and lit kilonovae. These stories do not fade when light fades. They remain written in atoms inside rocks, oceans, tools, and bodies. A stone, a drop of water, a strand of DNA, all are records. Think of the inventory you carry. Oxygen makes most of your mass, largely as water in your cells. Carbon forms the framework of your molecules. Hydrogen links back to the first minutes after the Big Bang. Nitrogen threads through proteins and genes. Calcium supports bone. Iron rides in hemoglobin to move oxygen. Trace elements, zinc, copper, iodine, phosphorus run enzymes and energy systems. Each came from a known path. Fusion in stars, shock in supernovae, or the rapid neutron capture of rare collisions. Each moved through gas and dust, then through planet building, then through the food and water cycles of Earth, and finally into you. These atoms did not travel fast. The universe worked on patient schedules. Clouds cooled, grains stuck, planetesimals formed and merged, crusts thickened, water cycled between ocean and sky. Biology emerged and used the same basic traits those elements had in every other setting. Carbon's 4 bonds, oxygen's role as an electron acceptor, iron's reversible grip on gases, calcium's stable salts, phosphorus's energy links. Life is not separate from physics. It is an expression that uses what physics offers. The same patience will carry onward. The atoms you borrow will return to air, water, and soil. The calcium in bone may enter limestone. The carbon in tissue may become part of a tree, a shell, or a layer of ocean sediment. The iron may rust into a rock or move again in another bloodstream. The cycle continues even as the rate of element making declines. The system recycles more than it creates. Across cultures, people felt this unity long before the details were known. The language of fire, water, air, and earth was an attempt to group the world. Measurements replaced those categories with a table of elements and with spectra that label light. The message stayed: one set of ingredients, many outcomes. Today we can tie each ingredient to a site and a process and still keep the sense of belonging. A universe without stars would be simple and quiet. Hydrogen and helium would drift. Few structures would shine. No water, no rock, no life. Our universe is different because stars exist, and because they fuse and return what they make. They laid the groundwork for planets and for the chemistry that runs cells. They also set the clocks by which we measure eras, the life of a star, the decay of an isotope, the fading of a supernova's afterglow, the expansion traced on the sky. Time and matter weave together. As the future unfolds, the weave will loosen. Star formation will slow more. The bright regions in spiral arms will thin. The faint red glow of long-lived dwarfs will carry the last visible light. Remnants will keep their orbits. Some planets will survive around cooling stars. Others will wander. Dust will still drift, but with no new stars to heat it, it will stay cold. The periodic table will still list the same entries, but the universe will no longer add to its shelves. Even then, the record will stand. Carbon in a rock will still point back to a core where helium fused. Oxygen in ice will still mark a past where stars ran hot. Iron in an old layer will still signal collapse. Gold in a ring will still connect to a crash of neutron stars far away and long ago. The facts will not need light to be true. They will be embedded in matter, durable long after the last bright point fades. Here and now, the kitchen is open. The sun fuses hydrogen to helium and sends light across empty space. In star-forming regions, gravity rolls gas into knots that begin to glow. In the aftermath of explosions, shock waves move through clouds and tip them toward collapse. Around young stars, disks of dust and ice build worlds. Water circulates. Carbon circulates. Life on at least one planet uses both, rearranging atoms into patterns that can copy and change. To be alive now is to take part. Every breath moves oxygen that a star made. Every glass of water mixes hydrogen from the beginning and oxygen from a stellar furnace. Every step presses on silicates, shaped in planet interiors from elements older than the Sunday. None of this is separate from the sky. It is the sky, rearranged into familiar forms. When you look up, The view is both present and ancient. Present, because starlight arrives continuously. Ancient, because that light left years or ages ago, and because it carries the fingerprints of elements born in deeper time. The Milky Way is not a flat picture. It is a system in motion, gas flowing, stars aging, dust forming and growing, remnants cooling, still rich with the chemistry that made your world. Other galaxies are doing the same, at their own pace, with their own histories written in spectra and in the ratios of their elements. The season we occupy will not last forever. That does not lessen it. It makes it clear. We live when the universe can still build, when it can still mix, when it can still light up new places with new stars. We can measure the paths of atoms, trace their creation, and read their ages. We can grasp where the oxygen in a breath came from, where the iron in a nail began, and why water behaves as it does. The more we learn, the more the pattern holds. Simple rules, patient steps, wide results. In time, the large motions will slow, and darkness will grow. The story will become quiet, with more memory than change. But the memory is enough to connect a future rock to a past star, a future ocean to a past nebula, a future cell, if any remain, to a long chain of events. The recipe will still be there, copied into matter, line by line. For now, the recipe is active. Stars write it with fusion. Supernovae underline it with shock. Collisions add rare notes. Planets collect the lines in stone, sea, and air. Life assembles sentences from the same alphabet and then reads them back as curiosity and care. We can choose to notice. We can choose to keep the record, to study the cycles, to understand our place not as a side from nature but within it. Hold that thought the next time you breathe, or drink, or look up. You are holding a small sample of the universe's work. You are made from its common parts, used in uncommon ways. You are living proof that hydrogen and helium, given gravity and time, can become water and rock, and that water and rock, given more time, can host awareness. The long arc of element making will one day quiet, but its results will remain carried in atoms, carried in worlds, carried in whatever minds arise to notice. And as the lights thin in ages we will never see, the old truth will still apply. Everything belongs to the same system. Everything is shared. Everything we hold began in a star and will move on. The fires burn now. The record grows now. We are here while the kitchen hums long enough to learn the recipe, to pass it on, and to listen as the last notes of this bright season fade into the long, gentle hush.